Let us now look at how do we find the shortest distance between two lines. So in this section, we will be majorly looking at what is known as skew lines. So what are skew lines? To understand skew lines, let's look at different kinds of lines that we can come across. So you might have, for instance, if I take a plane, so this plane extends infinitely in all directions, you might have two lines which are parallel to each other, right? So you might have parallel lines. If not parallel lines in the same plane, so in the same plane which extends infinitely in all directions, you might have two lines which are intersecting, right? You might also have two lines which are neither parallel nor intersecting. So you might have this third case, which is neither the first case nor the second case. In this case, you might have one line which is in the plane and another line, which is going away from the plane, right? This third case is known as skew lines. So lines which are neither parallel nor intersecting are called skew lines. So first of all, we are talking about shortest distance between two lines. This is one case, distance between parallel lines, which we will be looking next. So we'll be first looking at this third case, then we'll be looking at the formula for the first case, right? What is the answer for the second case immediately? The answer is 0, right? For this case, the answer is 0. That means there is no distance. Why? Because the two lines are intersecting at a point, right? So there is no distance. But if you talk about this is the perpendicular distance between these two lines. If you talk about this line, this is the perpendicular distance between the two lines, right? This particular line. And here, because they intersect at a point, so there they actually meet. So I will say the distance between these two is 0, or you will never come across a question like that. So if you come across a question where two lines are intersecting each other, so you must mark the option 0, right? So we'll be looking at the third case and the first case. Let's look at the third case now, which this third case, they are known as skew lines. So now let us look at this case. So I have two lines here, two skew lines, line B and line D. As you can see, these two, they seem to intersect here, but they are actually not intersecting. They are over each other, like they are non-coplanar lines. They are not in the same plane, right? So if I draw a plane around this CD, so if I draw a plane like this, this AB will actually be above that plane, right? So AB is not in the same plane, so it looks as if it's intersecting, but it's not intersecting. So let me write the equations of these two lines. So your first line is R bar is equals to A bar plus TB bar, because this line B, it passes through this point A. So there is this point A and there is this point C, right? So this first line passes through this point A and is parallel to the direction of B bar. So it is pointing in the direction of B bar. So obviously it's R bar equal to A bar plus TB bar, vectorial form. I'm dealing with the vectorial form right now. So vectorial form of the shortest distance between the two lines. So R bar equal to A bar plus TB bar. Similarly, here I can say that the second line, it's passing through C. So it's C bar plus some T dash into D bar, right? Some C bar plus T dash into D bar. Now, what I want is, I need the shortest distance between these two. So the only information that I have right now is basically this, the equations of these two straight lines. So with this, how can I find the shortest distance? So as you can see clearly in this diagram, if I join A and C, the vector which is joining A and C, so let me call it something like CA bar, right? So the one which starts from C and goes to A, right? So CA bar, I can simply write this vector as CA bar as A bar minus C bar, right? This is your vector which goes in this direction. But this might not be the perpendicular distance that I need. So I need the shortest distance, right? So if you keep going in this direction, you might hit this LM, which is exactly perpendicular to both the lines. So the speciality about LM is it is exactly perpendicular to both these lines. This might not be, so it might have some angle theta here, it might have some angle theta here, and these thetas might not be 90. But as I keep moving in this direction, this is where I will encounter the shortest distance. So what I need to do is I need to project this AC on this LM, right? So once I'm able to do that, because they're obviously the same direction, but I need to just project it. I need to project AC on LM, and then I'll be getting the length of this pink line. So let me first project this. So for that I will use the projection formula, and that is nothing but your A bar minus C bar, which is your CA bar. I will dot it with LM cap. So this is the shortest distance. So you're dotting it with LM cap. So it's like you have a vector A bar, you want to project it on B bar. What do? You take the angle, so you do mod A cos theta into B cap, where B cap is your direction, right? So mod A cos theta into B cap. So you basically take the dot product. So I'm doing the same thing here, AC, A bar minus C bar dot LM cap. So with this, what I'll be able to deduce is A bar minus C bar dot LM bar divided by LM mod, right? Because LM cap is LM bar by LM mod, and this is giving me something, right? This is giving me something. So LM is obviously a vector which is perpendicular to both this and this, right? So I have a vector B bar, I have another vector D bar. The speciality about LM is it is perpendicular to both B and D. So if I have a vector A bar, if I have a vector B bar, how do I get a vector which is perpendicular to both of these? Simply by taking the cross product, right? A cross B. Similarly, what I will do here is your LM is also perpendicular to both your B and your D, because it is D is pointing in this direction, LM is perpendicular. B is pointing in this direction, LM is perpendicular, right? So LM is perpendicular to the both. It's perpendicular to both. So I can simply write LM as B cross D. I can write LM as B cross D. Even if you don't write it as B cross D, and if you write it as something like lambda into B cross D, then also it won't make a difference to the formula, because now what I'll do is I'll substitute this in this. So you have A bar minus C bar dot lambda times B bar cross D bar, and you will divide this with mod lambda B cross D. So what you will do is you will cancel the lambdas, and the final expression that you will get is basically this. Let me just make some space and write the final expression. So your final expression will be A bar minus C bar dot B bar cross D bar divided by mod B cross D. Is it a vector or a scalar? Yes, the answer is a scalar, because this A bar minus C bar is a vector, B cross D is a vector. I'm taking the dot product of these two. So I'm getting a scalar on top. And this B cross D is obviously the mod of, so B cross D is a vector. I'll be taking the mod of that. So I'll get a scalar. So this is a scalar. This entire quantity is a scalar. It's a number. What does this number indicate? That number indicates the length of this LM. Right, that is what I was looking for. So I projected AC on LM and I'm getting the length of LM. So if I take the box product, so this is actually the box product. Now if you have a look at this topmost expression that you see, A bar minus C bar dot B cross D, I can write this as box A minus C BD, box A minus C BD, and below what you have is B cross D. So you have a B cross D here. So this is the formula that you need to remember. This is the vectorial form. So what all do I need to know for this? I need to know the point. I need to know the points through which the line is passing. A and C are the points, the position vectors are the points through which your line is passing. B is the direction of the first line, D is the direction of the second line. If I have the equations of the lines, I can put the quantities rightly in this formula. So basically this is the vectorial form, and from the top I'll get a scalar, from the bottom I'll get a scalar. If I take the ratio of these scalars, I will still get a scalar, and this scalar will indicate the length of this LM that I was looking for. This was the shortest distance between two lines in the vectorial form. Let us look at the same thing now in the Cartesian form.